So hi guys, thank you for coming. My name is Mario Fusco. I work for Red Hat, and I'm here today to try to do a comparison between the different concurrency model that are available now while working on the JVM. Okay, so first of all, I want to make crystal clear why we need concurrency and why we need to explore different concurrency models. Okay, I believe probably all of you knows this graph. That is the famous Moore's law that says that every 2 years, more or less, the number of transistors that we are able to pack on our CPUs doubles. Okay, but there is something that this graph doesn't say is that more or less here we're starting doing this by actually doubling the number of cores that we have on our CPUs. Okay, and unfortunately, in the meanwhile, we didn't change the way we write software, and this means that a biggest part of these transistors are now idle. Okay, because we are not leveraging this multiple core. Okay, to make even more clear what is the problem, you can say that for a long amount of time, the number of transistors we pack on the same CPU and the speed, the clock speed of the CPU grows up in the same way. But again, at some point, something happened. These two lines started to diverge, and then we have what I call the multi-core crisis. Okay, we have a different kind of hardware, we can have a different kind of machine, and we are not that good to use the full powerful of this hardware. Okay, so in the end, what typically happens in your CPU is something like that. You have one worker, and the other guys looking at it and say, "Come on, come on, come on," but not being very helpful, right? Okay, so we are on a mission, okay? We are on a mission. We want to avoid this situation on our machines, okay? So the goal is to do more effectively concurrency and parallelism that are two faces of the same coin, okay? And both those tasks are hard. Okay, are hard, I believe, especially for a reason, because historically we have a default concurrency model in Java. That is the one based on threads, on synchronization, semaphores, locks, and all those mechanisms that you know if you work with thread, if you write multi-thread application, okay? And this stuff, I believe, that sometimes is plain evil, sometimes is necessary, it is unnecessary pain, but what is really important is that I believe that is the wrong default, okay? I mean that we have many options, as you will see during this talk, and we take this option as the default option for doing concurrency on the JVM, and this is definitively the wrong default, in my opinion. Okay, let's try to figure out why I'm saying this. Okay, so let's try to do this mental experiment. Try to ask to typical Java developers what you think when I say parallelism. Okay, and the typical answer will be, of course, threads. Okay, and what you think when I say threads? And probably the typical answer is locks. Okay, and what are they for? And locks are there to prevent parallelism, right? So, do you see the problem? Okay. Okay, so just to make a comparison between the different model, I try to write a very simple code this code is not beautiful, is not the way I wrote it, but I wrote it in a way that looks like, let's say, anthropomorphic, okay? I want to mimic with my code what human will do achieving this task, okay? The task is, I want to sum up all our ages, okay? So in a typical thread-based application, what happens is that I have a blackboard. I write my age on the blackboard, and then he comes up and he erase my age, sum up his age, and write the total on the blackboard, holding the lock on the blackboard. At that point, he is the only user, the only one allowed to use the blackboard, okay? And if something goes wrong, if he if he breaks the locks in some way for some reason, you have a stale value, and you will have a problem. You will have the wrong result, okay? Okay, so this is the Java concurrency Bible, I think. But the reality is that I know, of course, I know this book on my bookshelf, but I know that when I feel the need that taking this book from my bookshelf is that because I have a problem, I have a very hard concurrency problem, I'm trying to figure out what's going on, and at that point, I know that I'm in big problem, in big troubles, okay? Of course, there are a few good practices when working with threads, okay? For example, probably all of you knows the Diner philosopher problem. So the way to avoid this is acquire the logs always in the same fixed global order, okay? Of course, you shouldn't call an alien method, do a callback to your user while holding a log, because you don't know what the user will do while in his callback, okay? And if you do this, if you give to the user control when you are holding a log, very likely it could had its own lock and probably cause a deadlock, okay? Possibly you should avoid blocking at all with atomic, for example. You probably should avoid creating your own thread, but you should use a pool of cached threads. You should, of course, hold the logs for the minimal amount of time, okay? Because again, when you are holding a log, means that that thread is the only thread that can enter in that piece of code, that can execute that piece of code. So you have to make that piece of code as small as possible to allow more thread to do more things in parallel, okay? And probably it's preferable to use interruptible logs instead of using the synchronized keyword, okay? But anyway, the bottom line of all these advices is that you have to know you have to learn the Java concurrency API, okay? And do some experiment, learn it very well to use them effectively, okay? But when you follow all these practices and then you design your multi-thread application, you design something like that, and it seems to work. But personally, at some point, what happens to me is that this is the result. Okay, I don't know if it's the same for you. Because the problem is doing concurrency with threads it's hard. It's really hard. Okay, so what are the pros and cons of using threads and logs? Okay, the pros are it's close to the metal. It can be very efficient. It can be implemented in a very efficient way, given the hardware. Okay, it's this is both an advantage and a disadvantage. Of course, it's a very low abstraction level. So this gives you full control. Okay, but again, you are working on at a very low level. The thread and lock are historically the concurrency model in Java just because it was the easiest ways to be implemented, okay? So they are easy to be implemented, so that's why they are there since the beginning of Java, okay? Again, as I said, being a very low-level abstraction is also a disadvantage because doing thread and lock programming is harder, and understanding the Java memory model is even harder. Okay, the communication between thread is doing mutating the value of variables shared among the different threads. Okay, threads are a scarce resource. You cannot instantiate. You cannot have 100,000 of threads on your JVM. Okay. And since it is based on this shared memory architecture, you cannot. You have to have everything on the same JVM. Okay, you cannot have distributed logs. Okay, in reality, there are a few tools, framework like Hazelcast or Terracotta that allows you to have distributed logs. But trust me, if you are using distributed logs, if you design your application with the need of having distributing logs, you are really doing something wrong, I think. Okay, and this is another very important point, is that testing is very, very hard. Figuring out if our multi-thread application is behaving correctly is hard, if not impossible. Okay, we have a test that runs okay 99 times out of 100, and the last time it fails exactly the same code, and it's almost impossible to figure out what's going on. Okay, so and this was the case. I was trying to fix recently a multi-threading bug. I was totally lost, and at some point my colleague, my friend Mark, wrote this sentence on the IRC on the chat, and I put it on the slides just because when you are trying to fix a multi-threading issue, at some point you really feel of being the matrix and try to figure out what's going wrong there. Okay, so why this happens? I believe that thread and locks stands to concurrent programming as assembler stands to programming. Okay, it's very low level. It can be very performant, but none of us does assembler or only assembler because it's the most performant thing, yeah? Right? Probably, I don't know, if you do real-time application, maybe you will write the 99% of the application in C++ or in Java, and probably you really want the last nanosecond on a specific feature, and you will write that feature in assembler, but it's not the default, okay? It is not the default for us to use assembler as programming language, but it is the default for us to use thread and locks as concurrency model, and this is the problem, okay? And so the situation is like that, doctor, it hurts when I do it, then the solution is simple, then stop doing it, right? Okay. Okay. So in some way, you can improve this situation probably by using Q. What is the advantage of using Q? Of course, you are decoupling the producer of a value from the consumer. Okay, and you are not communicated between threads by mutating the value of a shareable or of a shared variable, but you are doing it by putting that value on a queue and consuming that value from another thread. Okay, but these of course have all the other problems that, in my opinion, are high wake-up latency. There is no built-in failure recovery. That is a big problem. It is quite heavyweight, and it's monodirectional. Okay, so a thread send a value to a thread 1, send a value to the thread 2 on that queue, but to do the communication in the opposite direction, you will need an additional queue. Okay, and in reality, if you think about it, if you know the actor model, we will come back to it later. If you know the actor model is just a way of using queues in a more structured way. So probably it is preferable. Okay, so what is the main cause of the problem while doing concurrency with threads and logs? Okay, is that you are mixing mutable state with parallel processing. Okay, and this leads to non-determinism. Okay, this is the problem. Very simple. And to fix this problem in a structural way, you have to give up to one of these two things, okay? And personally, I don't want to give up to parallel processing, because if I do, it means that my multi-core CPU is totally useless, okay? So what I want to avoid is mutable state, okay? And avoid mutable state, trying to keep everything immutable, of course, drives to functional programming. Okay, that is the next topic of this talk. Okay, so what is functional programming compared to object-oriented programming? I think this is the best definition of the difference between the two. Okay, with object-oriented programming, you try to dominate, to master the complexity by encapsulating the moving parts, the mutable state. While with the functional programming, you try to minimize them, to avoid them at all if possible. Okay? And indeed, if you think about it, parameter binding is about assigning our names to things. That is pretty normal. But mutating variable is about is the opposite. It's about assigning things to names. And if you think that the second is a bit weird, probably it is because it is weird. Okay? Which are the dangers of having mutability? The problem is that even if you are very careful, you can have hidden mutability. Okay? So, for example, here I'm declaring this this variable final, okay? So this seems to be a thread-safe method, okay? In reality, it isn't, because I have an hidden mutable state. This class, that is a Java class, has an hidden mutable state. You cannot use it from multiple threads in parallel, because you will have wrong values, okay? So the typical way Java developers fix this problem is having a thread local and put in instances of this object inside the thread local. So you can have one of these objects for each thread. That is pretty crazy if you think about it. And causes leaks and stuff like that. Let me show you a second example. Here I have two methods. That one is mutating this list, and one is creating an iterator out of it, and they are both synchronized. Is this code thread safe? Of course it isn't. Of course it isn't, because when I call this method, the mutable state is escaping. So if I'm iterating this iterator while another thread, while somebody else is adding stuff to the list, I will get a concurrent modification exception. Okay? So for this reason, working with mutable state, reasoning over mutable state, it's pretty hard. Okay, so if you remember, I did that example about summing our age with the blackboard, and okay, let's suppose it's not a blackboard in this case; it's just a piece of paper. But the functional way of achieving the same result is that I take a piece of paper, I write my age on that piece of paper. I give this piece of paper to him, and then he destroy that old piece of paper, create a new one, blank, write the sum, and pass it through the other people inside the room. Okay, and everyone destroy the old value and create a new one. Okay, this is the functional solution. I'm not mutating what is written on the blackboard. I'm destroying the old value and creating a new one. Okay, and this leads to another important difference that has been introduced with Java, also in Java, with lambda expression with Java 8. Okay, that is the difference between external and internal iteration. Okay, this is very related to doing parallel computation with functional programming. Why is it? We are very used before Java 8 to this style of programming, right? So we have a list, we externally iterate the list and do something on this on each item of this list. Okay. So why this is wrong? Okay, I think I really understood. What's the difference between external and internal iteration? Looking at my 3-year-old daughter, Sophia. Okay, if you have a small child at home, you know that at the end of the day, the living room is full of toys, and of course, the girl has to put away her toys before to go to bed. Okay, so what happened a few months ago with my daughter Sophia is that I had to guide her, okay, to say her, what's on the ground? The ball. Okay, take the ball and put it on the box. And what else is on the ground? The car. Okay, take the car and put the car in the box. What else is on the ground? The doll. Take the doll and put it in the box. Okay, I'm iterating the toys and guiding Sophia from the external. Okay. Now I'm finally able to ask to Sophia, please put all your toys in the box. Okay, so I've been able to change the way Sophia put away her toys from an external iteration to an internal iteration. Okay, why this is important? First, because it saves me some work. Okay, I just can say put all your toys in the box, not one by one. But this is also even more important for a different reason. Since I'm not guiding Sophia from the outside, Sophia can autonomously decide to take the ball with one end and the car with the other end and put them together in the box, doing parallel processing, right? And this couldn't happen if I'm guiding her from the outside, okay? Or Sophia could decide to take the car first because it's closer to the box, and then take the doll later because it's further, okay? And so instruction reorder, if you think about it, okay? So this means that Sophia is able to do a lot of optimization that weren't possible if I was guiding them from the outside, okay? And this is exactly the same thing, okay? This is exactly the same thing because in this case I just can change the stream in a parallel stream, okay? Everything remains the same, and then this stuff is done in parallel, okay? Why this is possible again, and why this is not possible here? Because in this case, with the internal iteration, the library, the native Java API in this case, is in control of the flow. So it can take decision, okay? You are not in control of how the list is iterated. The library you are using is in control. So it can take decision at your place. Okay. And if you think about it, this is the best way to write parallel code, because you really don't care about parallelism in this case. It's exactly the same code, right? Okay, so what happens internally when I do this stuff? I had my list of attendees, and I want to sum their ages, if you remember. The Java 8 stream internally used the ForkjoinPool framework that has been introduced in Java 7. So the list is split in two, and then in two again, till we reach a reasonable amount of item inside the sublist. And then each sublist is processed on a different thread, and then the partial result of each thread is combined to obtain the final result. Okay, and this is for free. For your point of view, this is totally for free. Okay. One of the problem of this solution, of this code, is that, okay, so I'm using a thread pool. Which thread pool I'm using? Where this thread pool comes from? Okay, the fact is that the ForkjoinPool that is internally used by Stream come with a default forkjoin thread pool, and the Java 8 stream just use that pool of thread, and you have no choice. Okay, you have no control. So that pool actually becomes a scarce resource, meaning that if you have multiple parallel stream doing different operation at the same time, they will all use the same thread pool. Okay, so, and at the moment there is no way in Java to say which thread pool you want to use in a given parallel processing when performed by a Java 8 stream. Or this is partially true. In reality, a guy discovered that you can have some control. Okay, the fact is that if you create your own ForkjoinPool and submit the processing of the parallel stream to this ForkjoinPool, what happens internally is that you are no longer using the default ForkjoinPool, but you are using this one, the one that you just created. Okay, or you can do the same, or probably also in a nicer way using completable feature. The problem is that this feature is not documented. We don't know if this is a feature, if this is a bug, if this is something that will remain in Java 9. We don't know. Okay, so the suggestion is, anyway, don't do this. Okay, I tried it, it works, but probably it's not a good idea. Just because it's not documented what is the behavior in this case. Okay. So this also brings me to what I think is the essence of functional programming. And I believe that this method signature, it is the essence. Why I'm saying this? Because if you look at this signature, you will see that I'm passing two things to this sort method. The first thing is the data, is a list. Okay? The second thing is not data, is a behavior. Is the criteria I want to use to sort this list. Okay? So this is an example. The data is the person, and the criteria is that I want to compare them by comparing their age. Okay? And if you think this is really the essence of functional programming, because data and behaviors are the same thing. You are passing data and behaviors to a method exactly in the same way. Okay? And if you think about it, I didn't write in my former example map and reduce by accident. Probably this should remember you something if you know the map and reduce algorithm invented by Google, right? And what's the strength of the original? What was the main idea of the original map reduce? Okay, is that I have a lot of data to process. These data are spread on multiple machines and are very huge. So I have two options. I can move the data from a machine to another to do the computation on the second machine, or I can take the behavior, I can take the function that does the computation and just move the computation where the data are. Of course, the data can be terabyte, while the function could be 100 bytes. So probably you want to move the behavior, don't want to move the data. This is the big idea behind MapReduce. Okay, and again, you can do this because you are treating data and behavior, data and function in an isomorphic way. Okay, so let's see what are the pros and cons, in my opinion, of functional concurrency. Okay, so I said the main thing that you have to do if you want to do real functional programming is having immutability. And why you want to do that? Because immutability prevents any non-determinism, definitively. Okay. In my opinion, but probably you have to be used to it. The functional programming also leads to a declarative programming style that is more readable, in my opinion. Okay. Parallelize a pure function that doesn't have side effect is trivially easy, as you saw in the parallel stream example. Okay, you can have better confidence that the program actually behaves correctly, and as you saw in the example of MapReduce, you have great support to distributed computation. Okay, the disadvantages, in my opinion, are that functional thinking is still a bit unfamiliar to people used to Java and then to object-oriented programming. Okay, in many cases, in reality, it could be less efficient, and this is another. And one reason of this is inefficiency is that for the reason I said before, you are creating and destroying lots of short-lived objects, and doing so, you are putting more burden on the garbage collector. Okay. And as I said, you have less control probably because you are ceding control to the library, to the Java API. And okay, this is good because it's no longer your business, it's the Java API business, it's the library business. But in some cases, you would like to have more control and you can't. And this could be a problem, okay? And probably functional programming is also a great abstraction for parallelism, as you saw, but for concurrency, it's a bit hard. It doesn't fit very well. Like, this is true. Okay. So the third concurrency model I wanted to speak about is actors. How many of you knows actors? Okay, quite a few. Okay. So again, just to explain what the actor model is I have that the usual exercise that I want to sum up our edges. With actors, you have mutable state, but it is not shared. Okay. So what you do typically is that in this example is that all of you will send me a message, an SMS with your age, and I'm the only owner of the total variable, okay? And I'm the only one allowed to modify that variable. So that variable is mutable, but it's not shared. I'm the only owner. You cannot change it, okay? So this is what I'm doing here, okay? And why I think the actor model is really good, because if you think about it, the actor model, it is in reality what the object-oriented programming was intended to be. Okay, I believe that object-oriented programming is one, as we do it now, is one of the big misunderstandings in the history of engineering. Okay, and indeed, Alan Kay, that is the father of object-oriented programming, say that he did a mistake coining that terms, because he put the accent on object, while the real important thing is messaging, is how those objects talk to each other. Okay, so the object-oriented programming, how Alan Kay and the other Smalltalk guys that originally have in mind, is far more similar to the actor model than to what we intend now with object-oriented programming. Okay. Another advantage of the actor model is that in Java, typically we are used to do lots of defensive programming. We fill our code with bunch of try catch, if not null and whatever. Okay. And the idea of the actor model is totally different. You don't try to be defensive against error, because in reality you can't. Okay, so what you actually do is let it crash. Okay, let an actor crash, and why you do that? Because you have a supervised model, meaning that the actors are created with a hierarchy. So, and you can define what happens when an actor crash. Okay, when an actor crash, the crash is reported to his parent, and the parent can decide if he should himself die, or if he should just recreate the died actor, or if he should kill all his siblings and create them from scratch. Okay, so you have different policies, of course related to the task you are trying to achieve, and this means that you have a very good way of dealing with failure built in this model. Okay, so again, let's also try to underline which are the pros and cons of this model. Okay, so again, you saw that the state is encapsulated, and actors talk to each other, exchanging messages. So this could be very natural when you are implementing an application based on message flow. That is why I said that queues are just actors are just a generalization of queues, are just a way of using queues in a more structured way. Okay. You have built-in fault tolerance, as you saw. They are not a scarce resource, because you can map thousands of vectors on the same thread. Okay, so you cannot have a million threads on your JVM, but you can have a million actors. Okay. Another concept very important is that also distributed computing is built in, because you can have an actor locally on your machine, and an actor is running locally, remotely on another machine, and this actor can talk to each other in a totally transparent way, and you also don't know where the actors are physically located. Okay, and in some way, actors map the real-world domain model. Okay, there are some also some problems that are mainly related in how actors are implemented. By the way, you can use actors in Java, as you saw in my very small former example. One way to do this is using Akka. Akka is a toolkit, is a framework that is written in Scala, but it has a Java API that is the API that I was using there. But of course, there are some features that play well with actors in Scala, and you don't have them in Java. For example, pattern matching. Okay, so what you do is that you have in Java is that you typically have untyped messages. So you are passing an object as message, and what you typically do is a lot of instance of to trying to figure out which kind of message your actor received. Okay, it's easy to break the encapsulation. As I said, I'm as an actor, I'm the only owner of the variable, but it is not something that can be enforced. As much in Java, you cannot enforce immutability. Okay, so the message has to have immutable, otherwise the actor just won't work as you expect. But you cannot enforce immutability in Java. Actors are only, if you think about it, actors are useful only if they produce side effect, meaning that an actor can do just two things: can change his internal state or send a message to another actor. That are both side effects. Okay, composition in some cases can be difficult. Okay, and another important thing is that actors don't really prevent deadlocks, meaning that you can have also deadlock while using actor, simply because my actor is waiting a message coming from his actor, and his actor is waiting for my message, and they are all waiting for each other. So you can have deadlock, a sort of deadlock, also using the actors. Okay. So what I'm saying is just this: is that what is really important about concurrency is how you manage the state. Okay, and you have two degrees of freedom. Your state can be mutable or immutable, or can be shared or unshared. Okay, and the reality is that in this area, that is the threads area, you have a mutable shared state, and you are in the area of non-determinism. Probably, if you can, you should move in the green area by not sharing your mutable state, or I believe even better, by making your shared state immutable. Okay? Another model is the software transactional memory. What software transactional memory does is allow you to implement in your software the ACID model without the D. Okay, meaning that you have atomicity, consistency, and isolation. The one thing you don't have is durability. Okay, so what this means? This means that you are modifying a set of variables. Okay, and you want to do it in atomic way. When using a software transactional memory, you can do this in atomic way, meaning that the framework optimistically tries to change these two variables. Okay, and if it fails, it throws an exception and then retries automatically. Okay, so it is like an optimistic lock. It's like the optimistic lock you have on your database. Okay, it tries to do it. If there is no other thread working on this on this variable, everything will be okay, and I didn't acquire any lock. Otherwise, it will face, the transaction will face, everything will be rolled back and retried again later. Okay, so it's like a transaction. Okay, I used the multiverse for this example. That is an open source framework implementing this concurrency model. There are a few other of them. There is another one called Deus STM, and also there was an STM module inside Akka, but I believe they are no longer supporting it. Which are the pros and cons of this? Is that you can eliminate lots of problems related with the race condition without doing any synchronization, without acquiring any lock, because it is optimistic and not blocking. And if you think about it, most of you are really used to think in transactional terms. Most of you work with database and know what a transaction is, and know what happens when a transaction is rolled back. So it is very common for you to think in this term. The only difference, again, is that you don't have durability. Okay, the variables are in memory, are not written in the disk, but for the rest is exactly the same. Okay, and you know that you can compose multiple transactions. Running a transaction inside another transaction, this is pretty normal, and you can do the same. So composition is very natural. Okay. Of course, if you can have a high contention rate, you can have a lot of write collision, and this failure has to be retried again and again. This can be costly. This could lead to an unpredictable performance. And another important thing is that all action that you can do inside that atomic transaction, of course, has to be idempotent. I mean, they should be re-executed again and again and again, producing the same result. Meaning that I cannot send an email inside that transaction, because if that transaction is retried 3 times, I'm sending 3 emails. That is something I don't want. Okay, and even in this case, there is a very poor support for distribution. Okay, there are another 2 concurrency tool that I want to discuss very, very quickly. One is Future, or the Java 8 version that is even better, that is called Computable Future. A future, I think all of you know what is it. It's a value that will be, it's a value that is not present yet, but something that it is being calculating in this moment, and at some point in future will be available. Okay, with completable future, you can leverage the expressiveness of lambda expression, so you can do this stuff. For example, here I wanted to find the price of a product, but in my store the price of the product are expressed in euro, and my customer is asking me that cost in US dollars. So what it happens is that I can run to processing in parallel. I can ask to my store what's the price of that article in euro. And then I can ask to another server, what's the conversion rate between euro and dollars? And when all the value, both the value are available, I can combine them. Okay, so I'm in a very natural way. I'm running to quite long task in a parallel way. Okay. So the advantage of this solution is that you have non-blocking composition that is quite natural. The future can be freely shared among different threads, and it's quite easy to recover from failure because it's built in the completable future API. The drawback is that you have some callback L, as you can see. You have lots of function callbacks, etc. And debugging can be hard, and you have some problem if these closures are written against some variable that are outside the scope of this lambda expression. Okay, so my time is finished. This is the very last slide. It's about reactive programming. Reactive programming is the another emerging concurrency model. It has a few implementations. One of them is RX Java that I'm using in this example. There is Akka Stream and other implementation. What you do is that this is the you can think about an observable as a feature that can have multiple value, and the observable push the value to you when they are available. Okay, and so you can have you can have a very handy API. You can transform this value in many ways. So again, you have non-blocking composition, but this time with a richer semantic. As you can see, you can use the same method you normally use on a Java 8 stream, for example. Is event-centric and also has a good built-in failure system. Again, you can have a callback L. This sort of change your mental model because you are used to pull the value from an iterable, for instance, while in this case the observable is pushing the value to you when they are ready. And there could be a few problems if the usual problem when you have a fast producer and a slow consumer. Okay, so there is no one size for all solution. Okay, so you have to know all this model and find the best one. Okay, and my suggestion is try to keep everything immutable. If you can't use it, isolated mutability. Some tricks that are typical with sequential programming, like external iteration or using variables, are not very good when you do parallel programming. Try different solution again, and make it right first, and then make it fast, of course. And the last thing is that, as you can see in Java, you can have 6 or even more different concurrency model. So it's more important to be a poly-paradigm programming, known multiple paradigm, and because you can use all this paradigm with one single language. Okay. And that's all. If you want to know more about this topic, I suggest you these 2 books. And of course, I'm out of time for questions, but feel free to ask me offline. Okay, thanks.